In section 9.2, we're going to continue to work with our two variable linear systems of equations, but we're going to discuss an alternative method of solution, which is very useful, which is called the method of elimination. The goal in the method of elimination is to obtain coefficients on two variables in the system that are equal in absolute value, but have different signs. Okay. Again, to make a long story short, what you're looking for is, for example, if you have, like, let's say a 2x term, we would want for the other term in the other equation to be negative 2x. Or let's suppose if you had, let's say, like a negative 7y term in one equation, we would want for the second equation to have a positive 7y term. Okay. We can accomplish this if we need to by multiplying both sides of one equation by a non-zero number, or it's possible to multiply both equations in the system by some non-zero number in order to achieve this. After we have a variable that has equal and opposite signs, the next thing we're going to do is add the two equations together in order to eliminate one of the variables, which is yet another way that we can get to a single equation with a single variable. From there, we know what to do. We're going to solve that single equation for the variable, and then we can substitute that value into one of the two equations in order to find the value of the other variable. And then don't forget, at the end of the day, we want to write our solutions as ordered pairs x comma y. Again, the reason for the equal but opposite coefficients is that when you add objects like that together, they cancel and result in 0. So we know that 2x minus 2x when added together produce 0. Similarly, if you were to add negative 7y plus 7y, adding those together results in 0. Let's look at an example of this. Let's solve the system 2x plus y equals to 7, x minus y equals to negative 4 by using the elimination method. This is a really good first example because we're already kind of set up to where we need to be. If you look at the y variable in the first equation, we have a positive y. If you look at the y variable in the second equation, we have a negative y. Those two are already equal in magnitude but opposite in sign. So the next step is we're going to go ahead and we're going to add the two equations together. On the left-hand side, if I add 2x and x, that'll give us 3x. Positive y and negative y add together to give 0y, so those two cancel. So we're left with just an x on the left-hand side. And on the right-hand side, 7 plus negative 4, that's going to be positive 3. Okay, and this is exactly what we want. We now have an equation 3x equals to 3. To solve this for x, we just divide both sides by 3, and we get the x value is x equals to 1. So the x coordinate of our solution is going to be 1. The only thing that we don't have right now is we don't have the value of our y coefficient. To find that, all you need to do is take x equals to 1 and substitute it into any one of the original equations. Maybe I'll just plug it into the first one. It doesn't matter. Again, you have some opportunity and choice here. But if I take 2 times 1 plus y equals to 7, this would say that 2 plus y equals to 7. To get the y by itself, I'm going to subtract 2 from both sides. And so we get y equals positive 5. So we have the solution to our system. It's going to be the ordered pair 1, 5. This is our first example solving a system with the elimination method. So again, just in case if any of you are skeptical, there's always a way to check this. So let's go ahead and check this one together. So everywhere I see an x in the system, I'm going to put 1. Everywhere I see a y in the system, I'm going to put 5. Let's show that that ordered pair simultaneously satisfies both equations. This would look like 2 times 1 plus 5 equals to 7. And then 1 minus 5 equals to negative 4. And sure enough, 2 times 1 plus 5 is 7. So we get 7 equals to 7. And then 1 minus 5 is negative 4. So we get negative 4 equals to negative 4. So it does check out as our solution to the system 1, 5. Let's take a look at another one. We have 5x plus 3y equals to 6. And then our second equation is 3x minus y equals to 5. At this time, we don't have any pairs of variables that have equal magnitude but opposite sign. But notice that at least the y values have opposite sign. The first y has a coefficient of positive 3. The second y has a coefficient of negative 1. It's pretty easy to convert them to have equal and opposite sign. All we need to do is to create a negative 3 here for the y, and we can do that simply by multiplying both sides of that second equation by 3. So remember, whatever you do to one side of an equation, you have to do to the other side. This would give us 9x minus 3y equals, don't forget, you also have to multiply the 5 by 3 to get 15. I'm now going to write my rewritten second equation under the first. And now we should be able to go ahead and add them together. The equal sign comes straight down. On the left-hand side, 5x plus 9x, that's going to give us 14x. Notice the positive 3y, negative 3y cancel by design, so the y term is gone. And on the right-hand side, we have 6 plus 15, which is 21. So we get 14x equals to 21. We can solve this for x by dividing both sides by 14. That cancels. We get x equals 21 over 14. But notice that that reduces. Both top and bottom are divisible by 7. So that's going to give us 3 halves. To now find the y coordinate of our solution, all we need to do is take x equals to 3 halves and plug it into any one of the original equations. Maybe I'll plug it into the second one. So everywhere we see an x, I'm going to put 3 halves, like this. And now we just have to solve for y. 3 times 3 halves is the same thing as 3 over 1 times 3 halves, which would give us 9 halves. So we have 9 halves minus y equals to 5. We would now subtract 9 halves from both sides. Cancels, cancels. We get negative y equals 5 minus 9 halves. That's the same thing as 5 over 1. Get a common denominator, which is going to be 2. Right, multiply top and bottom by 2, we get 10 halves. 10 halves minus 9 halves is equal to a positive 1 half. And then to get y by itself, either multiply or divide by negative 1, however you like to think of it. And so we find that the y coordinate of our solution, positive y equals negative 1 half. So we have an ordered pair solution. It's 3 halves, comma, negative 1 half. Let's take a look at the next one. Here we have 3x plus 2y equals to 10. And we have 2x plus 5y equals to 3. Again, at this moment, we don't have any x values or y values that are equal and opposite in sign. So we kind of have our choice. We're going to take a little bit of work for this one. Let's say I want to get rid of, I don't know, maybe the x value. So I want to get rid of the x variable. So I want these two things to have equal but opposite coefficient. In order to do that, I need to find a common value that both 3x and 2x can go into. And that's going to be the LCM, which is going to be 6. So I can convert the first one. Let's multiply both sides of this equation by 2 to get the following. That's going to give us a 6x plus 4y equals to 20. And now I've rewritten the first equation so that it has a positive 6x coefficient. I now want to create a negative 6x because they need to be opposite in sign for the second equation. So I'm going to multiply both sides by negative 3. Negative 3 times 2x is a negative 6x. Negative 3 times 5y is a negative 15y. And then a 3 times negative 3 is negative 9. We've now successfully gotten to the point where our x coefficients are equal in magnitude but opposite in sign. So we can go ahead and combine these. 6x plus a negative 6x will cancel. 4y plus negative 15y will give us a negative 11y. And then 20 plus negative 9 gives us positive 11. So we have negative 11 equals positive 11. To get the y by itself, just divide both sides by negative 11, and we get y equals negative 1. To find the corresponding x value, we just need to go ahead and plug that into one of the original equations. I'll do maybe the first equation. So we have 3x plus 2y equals to 10. Everywhere we see a y, I can put negative 1, like this. This is 3x minus 2 equals to 10. Add 2 to both sides. That produces 3x equals to 12. Divide both sides by 3, and we get x equals to 4. So our ordered pair solution, again, don't forget to write your conclusion, x comma y is going to be 4 comma negative 1, and that's the solution to our system. Let's take a look at the next one. For this one, I can very easily get the x's to be equal and opposite if I simply take the first equation and multiply both sides by negative 3. If we do that, this is going to become negative 9x minus 6y. 4 times negative 3 is negative 12. The second equation is 9x plus 6y equals to negative 7. We've successfully created a situation where the x's have equal but opposite coefficients. So now I'm going to go ahead and add those together. Negative 9x plus positive 9x cancels. And notice that coincidentally, it wasn't our focus because we were worried on getting the x's to cancel. It turns out that the y's cancel as well. Negative 6y plus positive 6y cancels. So we're left with 0 on the left-hand side. And this is going to be equal to negative 12 plus negative 7 is negative 19. What we have as a result is a contradiction. We know that 0 is not equal to negative 19. And that means that this is one of those systems that will have no solution. You can either write it out in words, no solution, or you can use the empty set notation. Let's take a look at one more example here. In example E, we have negative 5x plus 6y minus 3. I believe this should say equals to 3. Sorry, that's a typo. That's equals to 3. And then we have 20x minus 24y equals to 12. I can get a situation where we have equal and opposite coefficients for the x simply by multiplying the first equation by 4. If we do that, that'll give us a negative 20x plus 24y equals to 12. And then we have 20x minus 24y equals to 12. And I believe for this one, I think this is a doubly typo. I think it was that negative sign was supposed to be with the 3. I think they're missing an equal sign in between here. So my apologies. This equation should say equals negative 3. So this is going to be negative 12. Okay. And I'll explain why I want that to be the case in a minute. When we now add these two equations together, again, the goal was to get the x's to cancel, and we were successful. Negative 20x plus 20x is 0, so that cancels. 24 plus negative 24, that also cancels. So we get just 0 on the left-hand side. On the right-hand side, we get negative 12 plus 12 also equals to 0. So we're in a situation where both variables end up canceling, producing us with a one equation that is actually true. Whenever that happens, this is the case where there's going to be infinitely many solutions. So be very careful here. Infinitely many solutions does not mean all ordered pairs. You can't plug any old order pair into the system and expect it to work. However, what this tells us is that any ordered pair that's on one of these lines will actually be on both of those lines. So this one will have infinitely many solutions, and the solution set is simply any ordered pair that satisfies any line in the system.